So today, as we talk about the chain rule, we need to first understand the concept of what is a composite function. Now, if you took college algebra, hopefully your instructor told you a little bit about what composite functions are. I know that's something we talk about in my class. And it's the idea that you've got a function inside of a function, okay? And so this right here, and I've got a new little tool that's kind of cool. Look at this. I've got like a, no, this is it. I've got a laser pointer I can use now. How about that? So what you see is whatever this function is goes inside your f function and is used for the x part. The entire function plugs in for the x part in the f function. So in general, this is how you would explain what the chain rule looks like when you have a function inside of a function. Now, what I'm going to tell you is this looks like a confusing mess. What I'm going to show you is something called a chain rule table that will help you stay organized, I think. But it is based on the idea that we have a function inside of a function. And so what that's going to tell us is we differentiate the outer function, but then we have to go back inside to differentiate the inner function as well. So look at this first problem that they've given us. The only thing we're going to try to do is put one function inside the other function. So if you're looking at this, it's telling us that g of x gets plugged in for x inside the f function. And here's what g of x is. Here's what, and they're using a different letter so you don't get confused. Instead of saying f of x, they're just going to call it a u here. So here's the idea. We're going to find f of, and we're going to put everything that g of x is in place of where the x would go. So g of x is 3x squared minus 7x plus 17. So far, does that make sense? Okay. Now, if I look at what the f function is, then whatever went in for the x is supposed to have what happened to it? Yeah, it's just cubed. So that means everything that went in for x, the 3x squared minus 7x plus 17, is going to be cubed. And that would be our composite function. All right? So far, does that make sense? We're going to do one more of those. Practice making the composite function. Okay? So if you look at this one, we've got f of g of x, and our f function is to take the natural log of whatever we're using for x, and our g function is another polynomial. So let's see if you guys can tell me what's going to go in for for x in the f function. Exactly. This part right here, right? The 4x squared plus 7x minus 35. So we're going to have f of 4x squared plus 7x minus 35. And now, if I plug that into the f function, that means I'm going to do what with it? I'm going to take the natural log of all that. So it just becomes the natural log of, and then I would put in the 4x squared plus 7x minus 35. Okay, so the idea of how to build a composite function, we're good, correct? All right, now we're going to practice how you would differentiate. And as I told you, I'm going to show you what I would call a chain rule box. It's simply a way to keep you organized. If you remember I think I've shown you a box you can use, say if you're multiplying a binomial times a binomial. Instead of having to use FOIL, the box is there just to keep you kind of organized. I think this is a tool very similar to that in concept, that it just gives you a more visual way to make sure you don't lose any pieces when you're working with getting the derivative. So what I'm first going to ask you, when you look at number 5, what do you see that should look kind of familiar here? Does this sort of look like the first function we built? It does, doesn't it? Because this would be what went in for x, and that entire thing got cubed. So here's the way we're going to have to think about differentiating it. Okay? If I make a table or a box, my entire function could be thought of this way. Think of what would be your outer function, or the very last thing that would happen in this problem. If I knew what x was and I was plugging it in, what's the very last thing that's going to happen? I'd have to plug in x everywhere. Would I clean up what's in the parentheses first? And then the last thing I would do is what? Cube it. So the outer function would be whatever is happening to what goes in for x in the f function. So in other words, I have something cubed, right? That's my outer function. There is something that's being cubed. Now the inner function is whatever is being cubed. It's what is inside the parentheses. So I would have the 3x to the 4th minus 5x plus 13. So far, does that make sense? We're just kind of breaking it apart to see what would have been the two functions that got put together to make this thing. So I know there was something that was cubed, and the something that got cubed was the 3x to the 4th minus 5x plus 13. Now, to use the chain rule, we're going to have to take the derivative of each of these. You got to take the derivative of the outer function and then come back and take the derivative of the inner function and multiply them together. So think of this open parentheses. There was something cubed. All right? Now, if I had x cubed, how do I differentiate that? Exactly. I'd pull down the exponent. It would multiply times the x, and then I would take away 1 from the exponent, and it would become a 2. Now, at this point, I can put back in what belongs inside that parentheses. What was that inner function? 3x to the 4th minus 5x plus 13, right? What?
In the derivative, you don't really need 13.
Well, but I haven't taken the derivative yet. I'm just putting back in what was in the parentheses. So you think of it, if it was a 3x squared, I haven't done anything to the x itself. All I've done is pull down the exponent. The x is still there being multiplied times the exponent, and the exponent got pulled down, and then my new exponent is 1 less than what I started with. So once I take the derivative of the outer function, I go back and I plug in the parentheses, whatever is over here, okay, because that's what went in. And now I'm ready to take the derivative of the inner function. So what is going to be the derivative of 3x to the 4th? 12x cubed. What's the derivative of minus 5x? Minus 5. And what's the derivative of 13? 0. So this is the derivative of the inner function. This first thing that we wrote down right here is the derivative of the outer function. My complete derivative is taking everything in this bottom row and multiplying it together. Now, the only thing I would recommend is just as far as the order you write it in, You can decide if you want to switch things around. So I could put the 3 first times, I could put 12x cubed minus 5 next, times, and then I would have the 3x to the 4th minus 5x plus 13 in parentheses squared at the end. If I wanted to clean it up just a little more than this, what else could I do? Is there anything I can distribute? Is it possible to distribute these two? Ah, I can. Now, I can't distribute with this one that has the square on it unless I expanded that out, and I don't want to do that. But it's also possible to write this derivative as 36x cubed minus 15. Now, that needs to be in a parentheses, okay? I distributed through that parentheses, but both of those terms would have to be multiplied by 3x to the 4th minus 5x plus 13 in parentheses squared, okay? And entering those in either of those two ways should be fine in my math lab. It's certainly going to be fine for me if you write it either of those two ways when we take the test. So far, are we okay? All right, let's look at another example. So this time we have f of x equals 4 times the natural log of 9x minus 7. Now, here's my question. Is this a product rule? The answer is no. If the 9x minus 7 was in front of the natural log, I would say yes, it would be a product rule. The 9x minus 7 is what we're taking the natural log of. But it's a chain rule problem because we're not just taking the natural log of x, we're taking the natural log of a factor that has x in it. Does that make sense? All right, that's what you got to watch for. So if we were to set up a chain rule table here, then I'm going to write my outer function. Tell me what would my factor with x in it, it got plugged into what? Think about outer function, inner function. What would be my outer function, the last thing that I would have to take care of if I knew what x was? I would plug it in somewhere, and then I would have to do what? Exactly. I would do 4 times the natural log of something, right? That's your outer function. I would have to know what x is, plug it in to that inside parentheses to find out what number it is before I can take the natural log of it. Now, what are we taking the natural log of? There you go, the 9x minus 7. That's my inner function. This is the key. You got to be able to see how to pull these apart into outer function and inner function. So we're ready to take the derivative now by taking the derivative of each of these that we've put into this box. So what would be the derivative of 4 times the natural log of something? Say it again? Well, it's not the something, right? If it had been 4 natural log of x, it would have been 4 times 1 over x. Since this is 4 times the natural log of something, wouldn't this be 4 times 1 over something? Right? And at this point, I want to go ahead and put back in that parentheses what the something is. What belongs in that parentheses? The 9x minus 7. Good. Okay. Now, differentiate 9x minus 7. It's just 9, isn't it? The derivative of 9x is 9. The derivative of negative 7 is 0. Okay, multiply across on that bottom row. Think of that 4 as 4 over 1. You can think of the 9 as 9 over 1. What's going to be my derivative?
4 over 9x times 7.
Okay, be careful. Remember, we're multiplying straight across. What would I get in the numerator if I multiply straight across? 36, right? 4 times 1 times 9 is 36 over, and what's in my denominator? That's it, 9x minus 7. Okay, you guys give me a little signal. Is this a thumbs up, thumbs down, somewhere in the middle? Okay, so far I'm seeing pretty good feedback. Let's look at this next one, and this is pretty similar to the one that showed up in our notes the other day that was kind of out of order, because you can see we have e raised to a power, but the power's not just x, it's some factor that has x in it, right? So, does that mean this thing looks like it's going to need a chain rule? Please say yes. Yes. Okay. Let's make our table. Now, tell me what you think would be my outer function. What would I write in this first box? 3 times e to the something. Put a parentheses there. Very good. And what is my inner function? What goes in the something?
5x minus 2.
Excellent. All right. We are ready to differentiate. So how do you differentiate 3e to the something? Jordan, go ahead and say it.
3e
To the something, exactly. Remember, e to the x differentiates as e to the x, and the fact that 3 is that scalar or that constant coefficient, I don't lose it, I just bring it on down. So that's going to be 3e to the something. Now, what am I going to put inside that parentheses?
5x.
Good, 5x minus 2. And now differentiate the 5x minus 2, and it gives me
5.
just 5. Are we ready to clean this thing up? I think so. Multiply straight across, what do you get? 15e raised to the 5x minus 2 power. Very good. Any questions on that? All right, time for another example. So as we look at the next example, notice that if we leave this written as a fraction, we're going to have to use the quotient rule. And it is possible for us to rewrite this so it won't be a fraction anymore. But in addition to that, we need to pay attention to the fact that there is a radical, and we don't want to leave it as a radical because we don't have any way of differentiating something that's in radical form. So if we were to take w over the square root of 4w plus 2, but think of that as 4w plus 2 raised to the 1/2 power, because that's what a radical is. It can be written with a fraction exponent. We could get rid of the fraction then if we were to take the 4w plus 2 and take it to the numerator, which means we'll raise it to the negative 1/2 power. Remember, when we pull it up to the other location, we will have the sign on the exponent change. So if it's a positive in the denominator, it's the same exponent in the numerator, except it's negative. Now as I look at that, I see that I have the product rule that I can use, because I have the first factor, which is the w, times the second factor, which is the 4w plus 2 raised to the negative 1/2 power. So I've got the product rule, but within the product rule, notice we're going to need chain rule as well. So let's start on this, and that would mean that if I'm taking the derivative with respect to w, and I'm looking up here at this rewritten form. Notice I haven't done any calculus yet. This has just been algebra to rewrite it in a form where I can now work on taking the derivative. With the product rule, the derivative is found by taking the first, which is a w, times the derivative of the second. Well, this is where the chain rule comes in. So if I come over to the side, and my function consisted of something raised to the negative 1/2 power, and that something was 4w plus 2, I can now take the derivative of each of those parts, and that will give me the derivative of this second term. So something raised to the negative 1/2 power is negative 1/2 times something raised to the, now remember, we have to subtract 1 from our exponent. And since we'll need a common denominator, that means we're actually subtracting 2 over 2. So our new exponent is the negative 3 over 2 power. And we're going to have 4w plus 2 inside that parentheses. So we've taken the derivative of the outer term. Now the derivative of the inner term, the derivative of 4w plus 2, first term, derivative of 4w is 4. The derivative of a constant is 0. So that's what we're going to have for the derivative of this second term. It can be cleaned up a little bit though. So if I were to multiply all of these factors together, notice I have a negative 1/2 times 4 over 1. I can reduce down by taking out my common factor of 2, and that will turn this into w times, I have negative 1 times 2, which is a negative 2, times, and then I have the 4w plus 2 in parentheses raised to the negative 3/2 power. So I've done first times the derivative of the second, plus I need to do the second factor times the derivative of the first. Well, my second factor, I just copied directly from what I started with, which is 4w plus 2 raised to the negative 1/2 power, times the derivative of the first. Well, the first term was just w, and if I take the derivative of w, I get a 1. Calculus is over. We have now used the product rule. We still have a little cleanup to do though. So if I write the derivative with respect to w, my first term is a negative 2 times w times this 4w plus 2 in parentheses to the negative 3/2. You might want to go ahead, take it back down to the denominator, and write it with a positive exponent. Usually we try not to leave answers with negative exponents if we can help it. Plus, notice if I multiply 4w plus 2 to the negative 1/2 power times 1, anything times 1 would be itself, and again, we can take that negative exponent, make it positive by moving it back down to the denominator, and that would give us 4w plus 2 raised to the 1/2 power in the denominator. That is one way that the answer can be written. There's actually a little more algebra that you could do to clean this thing up, but if you get this far with it, you should be good. Okay? Now, if you look at the next example, we do not have the product rule or the quotient rule, but I do think I'm going to have a chain rule. And that's because I'm taking the cubed root of something that has x as a factor in it. So I'm going to start this chain rule table. And that means, first of all, probably want to rewrite this thing without the radical before I go to the chain rule table. So if I'm taking the cubed root of something, remember whatever that radicand is, whatever is underneath that radical sign, will go in parentheses and it's raised to a fraction exponent, where your index is the denominator in the fraction exponent. So that's going to be raised to the 1/3 power. So if that's what I now am trying to differentiate in my chain rule table, I should notice I have something raised to the 1/3 power. And what's inside that parentheses is 2x squared minus 3x. So that's my function broken apart into an outer function and an inner function. Now I can differentiate. So something raised to the 1/3 power would turn into 1/3 times something raised to, now remember, we have to subtract 1 to get our new exponent. So since I need a common denominator, that means I have 1/3 and I'm subtracting 3/3. That gives me a negative 2/3 for my new exponent. And I will plug 2x squared minus 3x back inside that parentheses now that I've differentiated. But now I've got to go differentiate the second term. And 2x squared, when I take the derivative, will be 4x. Minus 3x, when I differentiate, turns into minus 3. So now all of this gets multiplied together to give us the derivative. And that would mean that if I were to multiply 1/3 times 4x minus 3 over 1, I could think of that as the fraction 4x minus 3 over 3. I just multiplied those two pieces together. Times, and then I would have 2x squared minus 3x to the negative 2/3 power. If I want to rewrite that so that I end up with a positive exponent, that would be 4x minus 3 over 3. And in the denominator with that 3, I would bring down my 2x squared minus 3x, but I would raise it to the positive 2/3 power. You could also take it back into radical form, but it's okay to leave it in fraction exponent form if you wish. If you had put it into radical form, that would have been 4x minus 3 over, we would have our 3 outside the radical, and then we would have taken the cubed root of 2x squared minus 3x, and that would have been squared. Notice it doesn't come out from the radical because it's a cubed root, and I only have 2 of those being multiplied together. So we have, sorry, I went one page too far. Okay, so let's look at this one and tell me, do you think we have a chain rule problem? If y is equal to the natural log of 3x plus 7, and then that whole natural log is being cubed. All right, so in fact, this one you're going to see is even more layers of a chain rule. If I were to ask you, what's your outer function? What would be the very last thing that's going to happen? Say it again. I got to cube everything at the end. So that's going to be the outer function, something cubed. Now, what goes inside that parentheses? The natural log of something. Oh my goodness. ln of something, because that something is not just x, it's a factor that has x in it. And then that inside something that I'm taking the natural log of is 3x plus 7. Look at that. We can get layers of chain rule. And that's another reason why drawing the little table can definitely make things a little easier. So, all right, let's get the derivative now. How do you differentiate something to the third? 3 times whatever something is, and what's my new exponent?
2.
A 2. Now, inside this parentheses, I need to put what? The natural log of, and I need another parentheses with the 3x plus 7, right? Sorry, that looks a little sloppy. I've got to get a finer tip on my stylus. Okay, I'm ready to differentiate the natural log of something. What does that differentiate as? 1 over something.
Which is
And that something was the 3x plus 7. And now I can differentiate the 3x plus 7, and it gives me just 3. And I can think of that as 3 over 1. And I'm going to write it that way because I think with all these fractions, I'm going to need to kind of keep up with that. So let's see if we can pull all of this out. F prime of x equals, what are we going to end up having in going across the top? Okay, the 3 times 3 is going to be a 9. And then what is, I guess we still need the natural log of 3x plus 7 squared, right? Oops. Oh, you know what? Wait a minute.
that's all.
Yeah, this natural log of 3x plus 7, it's not just the 3x plus 7 that's squared, it's the natural log of 3x plus 7 that's squared. So I'm going to put a bracket there to make sure I understand I've got to do all of that. So I've used this 3, and I've used everything here. What's the only part that's missing? Yeah, this denominator. So I can either write it as a fraction, put it over 3x plus 7, or I could put it as times 1 over 3x plus 7. Okay? Does that make sense? As long as we're keeping up with the pieces, we should be okay, right? All right, one more example and then we'll call it a day. So let me slide that up. The total cost in hundreds of dollars of producing X cameras per week is this function. So I have 6 plus the square root of 4x plus 4. And now notice there's a domain restriction. This is only good as long as you're producing how many cameras? Between 0 and 30. In other words, if I try to make more than 30 cameras, this function doesn't hold because probably I've maxed out my available employees or materials or something. So first question says find C prime of x. So can we differentiate this function? I think so. What are we going to need to do in order to differentiate it? All right, first of all, rewrite it without the radicals. So that would mean this C of x is equal to 6 plus, now how do I rewrite that square root of 4x plus 4? Make it what?
4x plus 4 to the 1/2.
4x plus 4 raised to the 1/2 power. Okay, now, can we differentiate? I think so. What is the derivative of 6? It is 0. Okay? Plus, now let's differentiate 4x plus 4 raised to the 1/2 power. Since we've talked about product rule, quotient rule, chain rule, do I need any of those to be able to differentiate this?
Chain rule.
It's a chain rule problem, isn't it? Because something that has x in it is being raised to the 1/2 power. So if I come over here and I take something to the 1/2, and that something is 4x plus 4, let's see if you can tell me what we're going to get when we differentiate. Something to the 1/2 becomes 1/2.
To the,
What's going to be my new exponent?
Negative.
Good, because I have to do 1/2 minus 2 over 2. I'm subtracting 1 from it. So I'm going to get a negative 1/2 for my new exponent, and that 4x plus 4 is inside the parentheses. And now differentiate the 4x plus 4. What does that give you? 4. Okay, if I multiply this back together, think of 4 as 4 over 1. What's 1/2 times 4 over 1? 2. So I have a 2, and then in parentheses I have 4x plus 4 raised to the negative 1/2 power, right? And the 0 plus that means this part just disappears, and I have 2 times. And I can either leave it this way, or if I wanted to take it back down to the denominator to get rid of the negative exponent, I could. And that would be my derivative. Now, if it asks me to find, we'll just do this first one and then we'll quit because we're almost out of time. C prime of 15. What does that tell me to do? And then we're going to tell what that means. So if I were to put in 15 for x, I'm going to have 2, and I'm going to go ahead and put this over, and let's write this as 4 times 15 plus 4 raised to the positive 1/2 power. And I know if something's raised to the positive 1/2 power, that's the same thing as taking the square root of it. So how much is 4 times 15? 60. And 60 plus 4 is, and what's the square root of 64? It's a perfect square. It's 8. And 2 over 8 reduces to 1/4. Now, see if you can interpret this for me, and then we'll stop. The total cost in hundreds of dollars for producing X cameras per week is this. We just found the derivative. The derivative is telling us what? The rate of change of, and this is in hundreds of dollars, right? So what does 1/4 mean? Very good. 1/4 of 100 is $25. So tell me in words what this means.
Produce 15 cameras, we need to pay $25 per week.
Well, at a production level of 15 cameras, the cost is increasing because it's positive, right? That's my rate of change. At the rate of $25 per camera. In other words, the cost of producing the 16th camera would be about $25. Okay? So we're at the point that it's costing about $25 a camera. And then if we plugged in 24, we would find out, what would you expect? Do you think the cost per camera is going to go up or down? Hopefully it's going down. I mean, if we're not lowering our cost per camera as we produce more, we're not doing something right in the business, or we've already passed our maximum level. Okay?